All right, let's work another Lewis dot structure for a different covalent compound. This time we're going to use CO, aka carbon monoxide, that deadly gas that can actually poison you, asphyxiate you, that means prevent you from breathing, and cause you to die. So this is a pretty serious one. The first step to figure out what's the structure of carbon monoxide is to figure out how many different atoms are in the structure, meaning we need to count any subscripts we see. Well, we don't see any subscripts, so we have one oxygen atom and one carbon atom. All right, done. Now, let's decide how many valence electrons are in each atom and total them all up. Let's go to our periodic table. We should see by now that since we are in column 16 or 6A, oxygen has 6 valence electrons, carbon is in 14 or 4A, so it has 4 valence electrons. So let's put a total up on our workspace here so we can remember. 4 plus 6 gives us a total of 10 valence electrons, 10, that we need to make sure we put in our structure. All right, this step is done. Then we need to determine the central atom. Well, in this case, we don't actually. We only have 2 atoms, so we can either write our structure OC or CO, and it really won't make a difference. They're just going to be opposite structures, right? If we flipped them around, it would be the same molecule. So in this case, this just isn't a concern of ours. We'll just set it up CO right next to each other. So this part is done. I do want us to go ahead and check the electronegativity of these atoms, though, because we're going to use that a little bit later in this process. So we remember, if we look at our table, electronegativity increases left to right and top to bottom, with the exception of noble gases that have electronegativities of 0. So oxygen is more electronegative than carbon, which means it is more likely to attract extra electrons and kind of be greedy about having electrons. All right, let's move on to step 4. Place lines between bonded atoms and subtract 2 electrons from the valence electrons total for each bond. So remember, a bond is the same thing as drawing a shared pair of electrons. We can just represent it more easily as a line. So let's go ahead and take away 2 from our total. So we have 8 remaining valence electrons to place. All right, now we're going to put dots around the outer atoms. Well, we don't really have outer atoms, so we're going to use the more electronegative atom, because if you're more electronegative, you're more likely to attract extra electrons and be really greedy about holding on to them. And then we're going to do that until all the valence electrons are gone. So we've got 8, so we're going to put 1, 2, one pair, 4, another pair, 6, another pair. You'll see that oxygen's all filled up. We can't put another pair on it, so we'll put our last pair over here on carbon. All right, that part is done. We have put all 8 electrons somewhere. We've run out, but we're not done yet. We need to turn lone pairs into double or triple bonds until we have a satisfied octet rule. So let's check. Do we have a satisfied octet rule for each atom? Now, oxygen has 2 coming from the bond, 4, 6, 8 total electrons, so it's good. It's happy. What about carbon? Carbon also has 2 from the bond. Remember, the bonds are shared. So 2 from the bond and 2 from a lone pair. It only has 4 out of 8, is not happy yet. So let's turn some of these lone pairs that greedy old oxygen is hogging and make them shared electrons in a bond. All right, and recount. So oxygen has 2, 4 coming from the bonds, 6, 8, it's still happy. Is carbon happy? It has 2 from one bond, 2 from another bond, and 6 from the lone pair. So a total of 6. It's still not happy. So let's make oxygen give up another lone pair. All right, and recount one more time to see if we're good. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. It is happy.